So this video is going to cover Unit 2, and the first thing we're going to talk about is just some basic terminology like atoms and molecules. So just remember, atoms are a single element, and molecules are when they bond together. And then we have special names for some of them. So a compound is two or more different elements. And then we do have some elements that bond to themselves. Those are the diatomic elements. So remember, we have our little saying, Brenn-Klahoff, that we can use to remember that. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and then fluorine. So if you kind of say all those letters together, it sounds like Brenn-Klahoff. So that's kind of the way that I remember them. We also discussed the difference between a pure substance and a mixture. So just like the picture is kind of showing you, a pure substance is where you just have one thing. So we can either have one element or one compound, but you just have one thing in the solution or in the container. A mixture is when we have two or more. And you can see we have a homogeneous mixture. That's where everything is evenly spread out. And then we have a heterogeneous. That's where you can kind of see, let's say, separation. Okay, so we can see the different components. We can separate them in different ways. So filtration is good for heterogeneous mixtures because it can let the a part that's soluble kind of flow through the filter, and then it can kind of keep this one substance up here in the filter. So it can kind of separate them that way. So just make sure you know heterogeneous is good for filtration. This was like our sand and the salt water when we did this in the lab. Then if we want to separate a homogeneous mixture, we can use evaporation. So this is when we could take the salt solution and then we see the water is evaporating and then we're just left with the salt. So remember, evaporation is great for homogeneous mixtures. That way we can just get rid of the water and then leave whatever the substance was that was dissolved. You do need to know about the atomic structure. So remember, atomic number is our protons or our electrons. So when we have a neutral atom, we know that those are equal to each other. Our protons are our positively charged particles, and our electrons are the negative charge. Neutrons are neutral, and it's the neutrons and protons that make up the mass number. So you can if you can remember, the nucleus is the mass. We know the electrons are not in the nucleus. We know that they're floating around the outside. So that has to leave you with the protons and the neutrons is the only other thing. Okay, so example, oxygen. We know this is the atomic number. So oxygen has 8 protons, 8 electrons, and then the mass number, we can round that to 16. So we know that 16 has to equal the protons plus neutrons. And we already said we have 8 protons, so that means we're left with 8 neutrons. So we can subtract your mass number and your atomic number, and that will tell you the number of neutrons. When we're looking at an element that has, it's the same element like hydrogen, but they have different number of neutrons, that makes it an isotope. So here we have 3 different pictures. These are all isotopes of hydrogen, and then they've just given them little fancy names to specify. You don't need to know those names, but we can write them differently so we know that they're isotopes. So we can see that it has this number on the bottom is our atomic number. That's telling us that it has 1 proton. And then the number on the top is our mass number. So here we can see that this example only has 1 proton and 0 neutrons. This example has 1 proton and 1 neutron, so that's how we get a mass number of 2. And then here we have 1 proton and 2 neutrons, and that's how we get a mass number of 3. Okay, so these are all isotopes. You do need to know this definition for isotopes. So here, just calculating average atomic mass, we can do that for lithium. So remember, we have 2 different isotopes, and we're given the abundance. The trick we want to do is we want to turn this percent into a decimal in our formula. So we can just take, excuse me, we're just going to multiply these together. So we'll do 6.02 times, and remember, I want to turn this into a decimal from percent. So if we can remember, percent is out of 100. 100 has 2 zeros. So we're going to move our decimal 2 places. So that's 0.075. So we're going to multiply those 2 together. Then we're going to multiply the next 2 together. So again, 100 has 2 zeros. So I want to move my decimal 2 places. So that means we're multiplying it by 0.925. And so when I multiply those and then add them up together, it's going to give me the average mass. So if I type that in my calculator, 7.02 times 0.925, that leaves me with 6.945, which if we look at the actual mass number on the periodic table, we're pretty much on the nose. So you do need to know how to do this formula. So if you just remember, multiply the mass times the percent, and then we're just adding them up. Just make sure you remember to move your decimal, okay? If you don't, you'll realize that this number is way too big. You'll get something like 694, and we know that that's way too big to be on the periodic table, so you can kind of think about moving your decimal at the end. The next thing we really went over were electrons. So we did talk about the electron configuration, and this is just kind of where the electrons are inside the atom. So we know that energy levels get further and further out as we go down the periodic table. As our atoms are getting bigger, they're getting more energy levels, and these orbitals just show the path that the electrons move. So if I have an electron in the 1s orbital, it's just moving around in a circle. So it's just moving in a circle, round and round and around. When I have electrons in the p orbitals, they're moving like a little figure 8. So one will move kind of flat, one kind of moves up and down, kind of sideways, but they're in this little kind of figure 8 motion. Once we start getting into the D and the F sublevels, they start taking on these really weird pathways. You don't necessarily have to know the shape of D and F because they get kind of funky, but we do need to just know how to write the electron configuration. So we have some examples here. So if I have chlorine, which is right here, so the first thing I do is find my element, okay? And then remember, we always start at the beginning, just like we're reading a book at the top left. And then you'll have your, I don't think I have it on this slide, but you'll have your cheat sheet, the laminated configuration card that you can use on the final, so you can just follow along. But we're just going to count. So these 2 boxes, that's 1s, and since there's 2 of them, I put a little 2, and then I'm done. So now I need to move down to the next row. So here is 2s, and there's 2 boxes, so I put a 2 at the top. Now I'm at 2p. So again, this is the second energy level and the p sub level. So 1, 2, 3, 4, 5, 6. So 2p6. All right, I'm at the end of that row, so now I can come down to the third energy level. So I'll write a 3. We're on the S again, so 1, 2. 3s, it gets a little 2. Now we come over to the P, so we're still on the third level with P, so we want to count how many we have. 1, 2, 3, 4, 5. Now I'm at chlorine, so now I'm going to stop. So now I just write 3p5. That is my electron configuration for chlorine. Now we can write something called the noble gas configuration. Okay, so if we wanted to do that, again, we have to make sure we know where we are. So there's my chlorine. And then to find the noble gas, we're just going to go one row up and find whichever element is on the very end of our row. These are the noble gases in this column here. So we're just going to go up one row and then to the end. So my noble gas configuration would be neon. Okay. And then it's like I'm starting there. So I'm writing neon, and then now I just go down to my next row. So I'm at 3, and then I just keep going. 3s2, and then I go over to 3p, 1, 2, 3, 4, 5. So 3p5. So this is just kind of giving us a shortcut, a new starting point. Instead of starting at the very beginning, we're just going to start one row up and all the way at the end, okay, at our noble gas. If we were to do arsenic, arsenic is right here. So let me erase all of this so we're not confused. So here's my arsenic. I'm just going to, again, start at the beginning. 1s, 1, 2, and then I'm here, 2s2, and then I'm coming over, 1, 2, 3, 4, 5, 6, so that is 2p6. Right, so I'll go ahead and number my energy level. So there's 3, there's 2 S's, here's my 3 P's, there's 6 of them. I'm not at arsenic yet, so I'm just keep going down. I'm at 4, S, 2, and then when we get to the D, remember it's it kind of goes backwards 1. So this is really 3D, and again, this is labeled on your electron configuration card, so you don't really have to remember this, but you just have to know how to fill it out. So it says 3D, so we're just going to count 9, 10. So there's 10 of those, and then this goes back up to 4p, 1, 2, 3. So I just write 4p3, and that's where I stop. To do my noble gas configuration, let me erase. So here's arsenic, and then remember I'm just going up and over. So here's my noble gas. So I'm going to put AR in brackets. And then remember, this is just like we're starting here. So I just come down to the next row, 4, and then I keep going. S2, again, this is 3D, and there's 10 of these, 10, and then 4p3. Okay. All right, for our periodic trends, we are going to relate everything to 2 things. We want to look at energy levels. Okay, we know that my energy levels increase as we go down. So every row tells us how many energy levels we have. So on the first row, we have 1 energy level, 2 energy levels, 3, 4, 5, 6, all the way down to 7 energy levels. Okay, and then we want to look at our number of protons, right? And we know that our number of protons increase as we go this way because our atomic number is getting bigger. So we want to talk about how all of our trends, right, it all comes down to the force of attraction. Okay, how good is, if this is the nucleus, right, how good is it at attracting these little electrons that are floating out here on our outer energy levels, okay? So let's look at atomic radius, right? So we know that as we go down, right, our energy levels are getting bigger. So more, we'll say more energy levels. Okay, so that means that, this atom has 1, this one has 2, this one has 3, this one has 4. You can see I can't even keep them in the box anymore, right? So we're getting bigger. The size, more energy level, bigger size or radius. Okay, it's getting bigger as we go down. As we go across, so all of these on this second row, they're all going to have 2 energy levels. Okay, that's not changing. So my energy levels stay the same. So as we go across, remember we're comparing our protons. So over here, as we go this way, right, my protons are getting bigger. So that means I have a stronger magnet. Okay, so that means that my size is getting smaller. Okay, so it's literally like the magnet in the center is pulling those electrons in. It's like squeezing it together. Okay, so it's getting smaller. Ionization energy is the energy required to remove an electron. So we want to think about if it has a small force of attraction, okay, it's easy to remove. So that means low ionization energy. Okay, so if we think about our chart, right, as we go down, we know we're getting more energy levels. So that means those electrons are getting further away. Okay, that means that I can't hold on to them very well. So if they're getting farther away from me, they're going to be easy to take. So this would be, we'll say it decreases ionization energy, okay, as it goes down. As we go across, okay, our protons are getting stronger. So like, again, we can think of it like this one. We have the same number of energy levels all the way across here. It's 2. So the atom's the same size. All these electrons are the same distance apart, but my magnet is getting stronger as I go this way. So stronger magnet, so more force of attraction, right? That means it's going to need more energy to be able to remove that electron, because I'm holding on to it tighter, okay? So overall, we can think of it like, let me change my color to something. I'll use that. Our energy is going to increase, okay, as we go up, because we're getting either smaller, right, fewer number of energy levels when we go up, or we're getting more protons. So we're increasing our ionization energy. For electronegativity, this is attracting electrons. It's almost the opposite definition, but it works the same trend-wise, because if we're attracting something, that means I want to be able to hold on to it or pull it closer to me. So I need a stronger magnet, right? So if we're thinking about our energy levels, as our energy levels increase, our attraction gets weaker. So that means that we have low electronegativity, because I can't attract anything, right, if it's far away from me. As we're going over this way, my protons increase, my force of attraction increases. So that means I can attract electrons pretty good, okay, because my magnet is getting bigger. So again, we are increasing I'll change it where you can see it. Increasing as we go up, because we're getting smaller. fewer energy levels, or we're getting more protons for a bigger magnet. Okay, so that's the end of this video. The second part of part